Gnanam paramam dhyayam. Knowledge is supreme.
In the last lecture, I have defined what are algebraic elements over a field, and I have given some examples. Today, I will give a characterization of algebraic elements. This will allow us to examine whether some given element is algebraic or not in an efficient way. Okay, so let us recall our notation was K is as usual our base field, and let me remind you once more, we are considering K algebras. A is a K algebra. Arbitrary K algebra. It may be a field, may not be a field. It may be integral domain, it may not be integral domain, and so on. A typical example, we saw that in case of commutative, for example, we could also take A equal to K power n, where n is some natural number. This is a K algebra. The addition is component wise and multiplication is also component wise. In particular, see, this is 1 1 1, this is a multiplicative identity, and 0 0 0 is the additive identity. Anyway, so how did you define an element x in A is called algebraic over K. If we have looked at the substitution homomorphism epsilon x, this is a homomorphism from the polynomial algebra in x over K to A. The homomorphism is just evaluating a polynomial at given x. So for that also you could also give only value where capital X go, and then once you want the K algebra homomorphism, then it is dictated where the arbitrary polynomial will go. So if I map x to small x, then f of x, arbitrary f, has to go to f of small x, because we want K algebra homomorphism. Because once you know where x go, it is clear where x square will go, and it is also clear where linear combination will go. So this K algebra homomorphism, and if the kernel of this x is algebraic over K, if the kernel of this substitution homomorphism is non-zero, then we say that it's algebraic over K. So, and we want to characterize this in an efficient way, easier way. Okay, for that, let me just set up some notation. We have seen earlier that this kernel epsilon x or Ex is an ideal in Kx, and we know it is a non-zero ideal assuming x is algebraic, and we have seen the ideals in the polynomial ring over a field K. K is a field is very important. This is a field is very important. So such non-zero ideals are generated by a single polynomial, and that polynomial is also uniquely determined by this ideal if you assume that the generator is monic. So this is generated by, I will use this notation, mu x with unique monic polynomial mu x in kx. This polynomial is called minimal monic polynomial of x over k. Strictly speaking, I should also use, instead of mu x, I should use mu x k, just to keep track where the coefficients are. But when the context is understood, it is better to simplify the notation by dropping that k. Okay. So, now what did we learn in the first course on algebra? That whenever you have a ring homomorphism, then the kernel and image, how are they related? Isomorphism theorem says that if I take this ring Kx, this K algebra Kx, and go modulo the kernel which is generated by mu x, this is isomorphic to the image of this epsilon x, which is a sub algebra of K A, because this map is from epsilon x is from Kx to A. So, image is definitely a sub algebra. This is a K sub algebra of A, and this isomorphism is a K algebra isomorphism. But you know what is the image? Image also you can describe neatly. So, the image is nothing but, image of epsilon x is nothing but, it is generated by x as a algebra, because, so what is the image of this? These are all those polynomials evaluated at x, where f varies in kx. This is the image. So, this is precisely k small x. And what is this by definition? This is the smallest K sub algebra of A, because once x is there and it is a sub algebra, all polynomials in x is also there. The only thing we have is two polynomials may give the same evaluation, but may be different polynomials. So, this is the smallest K sub algebra of A containing x. Once it contains x, it contains x square, it contains x cube, it contains all powers of x and also their combination. So, it is in particular it is a sub algebra. Therefore, our isomorphism theorem tells Kx mod ideal generated by mu x, this is isomorphic to K small x, which is a sub algebra of A. This is a K algebra isomorphism. Once it is a K algebra isomorphism, it is also K vector space isomorphism and isomorphism as rings also together. So, therefore, because it is a vector space isomorphism, in particular their dimensions are equal. In particular, dimension of O as a vector space over K of this Kx mod ideal generated by mu x is same as dimension of as a vector space Kx. We have this, but between the two we know this quotient ring very well, because mu is monic and we can compute the dimension easily. So, let me state let me remind you, this already we knew from your basic algebra course. So let me state it as a lemma, and lemma I will state it more generally. So this is a lemma. So f is monic polynomial in Kx, and in this K may not be a field. Monic is very important. Monic polynomial. Let f be a monic polynomial in Kx. K, assume K is a field, or more generally any commutative ring. Then Kx mod ideal generated by f is a finite dimensional K vector space. If it is not a field, then one should say it's a free module of finite rank, but I am not going to write it here. I will just say it orally because we don't need in this course. Maybe when I need it I will say it. Of dimension equal to degree of f. In fact, we can give a basis. If small x equal to the residue class of capital X modulo f, that means in this ring Kx modulo f, then 1x up to x power n minus 1, where this n equal to degree of f is a K basis of this quotient residue class algebra Kx mod f. Proof: this is immediate from what is called division with remainder. That is immediate because we know that division, the remainders are unique, and remainders will have smaller degree equal to the degree of f because we are dividing by f. So therefore, remainders can have at most degree n minus 1. That means mod f, the remainder, is a linear combination of this, and it's unique because the remainders have degree less than n degree of f. That is the proof. So in particular, our problem therefore what we know 5. Therefore I will summarize it here. If x is in A, is algebraic over K, then dimension of vector space dimension of the subalgebra generated by x is same thing as dimension of the vector space Kx mod the minimal polynomial, which is equal to degree of the minimal polynomial. This is very, very important. So dimension Kx, this formula. So 1, if capital A is a finite dimensional algebra over a field. Okay. Then every element of A is algebraic element and its minimal polynomial has degree small or equal to the dimension of A over K. Smaller equal to because the minimal polynomial, the degree of the minimal polynomial is dimension of the subalgebra, not dimension of A, but dimension of the subalgebra. Subalgebra generated by X. So A may have more dimension, but this will, for example, so let us see explicit example. If I take A to be equal to say K power n, this is a finite dimensional algebra over K, namely dimension is n. Standard E1 to En is a basis, so the dimension is n. Now suppose I take an element A1 to An. This is my element A in A. Then we know A is algebraic. Because A is finite dimensional, but we don't know what is the degree of the minimal polynomial. So let me write a recipe. How do you find a minimal polynomial? So minimal polynomial you want to find the following. So you have this A. So think of linear. So look at the map K power n to K power n. A to A. Let me write A. A equal to K power n to A. And the map is any x going to A times x, multiplication by A. This A. This A is fixed, arbitrary element is mapped to multiplication by. This map I am going to denote by lambda. Lambda is for left multiplication. This is a left multiplication by A. So it is clearly K linear. This is a K linear map, and therefore I want to use some linear algebra. So this lambda A therefore is an endomorphism of the vector space A over K. Endomorphism means the map from A to A, and the suffix here means it is K linear. So it's a map of the vector space. So we know, because what do we know? We know that this map satisfies Cayley-Hamilton. Last time also I said that Cayley-Hamilton says the characteristic polynomial of lambda A, this is the standard notation, this satisfies lambda A satisfies that means this is 0 as a map. So this is a polynomial, and in that polynomial I have substituted this linear operator lambda A and it is 0. That is precisely what Cayley-Hamilton theorem says. So therefore in any case what the checks is lambda A is algebraic. A is algebraic over K, but minimal polynomial is the generator. So by definition mu of lambda A is the minimal polynomial. So minimal polynomial divides the characteristic polynomial, and because this kernel of what did I call it, epsilon A homomorphism, this is precisely generated by mu of lambda A and chi of lambda A is an element here. So therefore mu divide this in kx, and our problem is to find this, because this will give the degree of, this will tell us what degree polynomial A satisfies. So how do you find a minimal polynomial of the linear operator lambda A? I have to find the matrix of lambda A. And how do I find a matrix of lambda A? I take a basis, fixed basis, and see where that basis goes and write down the matrix and then find a minimal polynomial of that matrix. So therefore I will use the basis E1 to En. This is a basis of that k power n, standard basis. This is a standard basis of k power n, and I have to know where do this go under multiplication by A. So under multiplication by A, this goes to A times E1, but A times E1 is the first coordinate of A1, A times E1. So A1 A to An times E1, E1 is 1 0 0 0. See, this is A1 An, and this E1 is 1 0 0 0. So when I multiply component with, I get only A1. Strictly speaking, I should write it as A1 times E1. So where do En go under multiplication by A? That is An En. That is how it goes. So what is the matrix? Matrix is therefore the first vector should go to the column. So that is A1, E1 only. So 0 0 0. Next one will go to A2 E2. So that is 0, A2, 0, and so on. The last column is 0 0 0 0 0 An. So therefore the matrix is a diagonal matrix where it is easy to compute what is the minimal polynomial. And the minimal polynomial is precisely the product of the distinct factors. So I will write an answer on the next page. So the minimal polynomial therefore is, minimal polynomial of lambda A is product x minus a I j. This product is running over I1 IR n, where AI1 to AIR are the distinct components of A, which is A1 to An. So for example, if I take n equal to 2 and A equal to 1 1, the number of distinct components are only 1. So R is 1 in this case, and only one A, that is, and the minimal polynomial of lambda A will be just x minus 1. Whereas if I take A equal to 1 2, then the minimal polynomial will be equal to x minus 1 times x minus 2. In this case the degree is 2, in this case the degree is 1. The vectors, the algebra we are working with, A equal to k power 2, so this is 2 dimensional. In this case, the subalgebra generated by A will be just k A, and this will be proper because this is 1 dimensional, and this is the 1 dimensional because the degree is 1, and we have seen the subalgebra has a dimension equal to degree of the minimal polynomial. So this is proper. In this case it is 2 dimensional, therefore it has to be equal. This will be equal to k A in this second example. So this is how we compute many things. Okay, so this also tells us, this also asks the question, this also allows us to ask the question. So this is a question. So let A be a finite dimensional K vector space. Then we know that every element of A is algebraic over K. We know that. Question is, when does there exist an element small x in A such that A is equal to subalgebra generated by X. So such an element is called, so such a is called simple extension of K, and that element X is called a primitive element. Element of A over K. Simple extension and primitive element. And one of the main important observation of Galois that whenever you took an extension of Q, finite extension of Q, they are all have simple extensions and they have a primitive element. And one of the main problems in the Galois theory was how do you find that primitive element? And how do you use that primitive element to compute Galois groups? This is what we will also do it. So in this case, we know that in this case, in the two-dimensional case, where field has at least two elements, so you can always find, for example, A2, K2, A equal to K2. K is a field. So field has at least two different elements. So there exist A1 and A2 in K, which A1 is not equal to A2. And then this is simple. We have just checked that this is simple because this is as an algebra over K generated by A1, A2, where A1 is not equal to A2. But for example, you will have to know whether K3 is always simple, and you will need at least three elements different. And obviously you can write down an example where, for example, you can take a field Z2 and you can take Z2 cube. Then here, no matter what you do, the three tuples, at most two will be different. And then we know in that case, the minimal polynomial can have at most degree 2. It can never be degree 3, whereas the dimension of the algebra is 3. So this algebra is, for example, is not simple over Z mod 2. So over a finite field it becomes more difficult. Okay, for finite field we will have to use something else. So I will take a break and then we will continue this discussion.